So this is example 8-8 from the book. So we were asked to transform a load impedance of 60 minus J45 to an input impedance of 70 plus J90 with a system characteristic impedance of 75 ohms. And we were asked to use figure A. So that's what we're going to do. We are being asked to transform the load impedance seen looking into the load to an input impedance of 60 minus J45. So the addition of this stub network is going to transform our load impedance to some intermediate impedance. Let's just call it Z1. So in order to solve this problem, we're actually going to have to figure out what that intermediate impedance is, because there will be a reflection coefficient that corresponds to this intermediate impedance, and we're going to have to use that reflection coefficient in order to figure out, in order to in order to make use of the constant VSWR circle as we move along this series transmission line here. Okay, so figuring out these intermediate parameters is the first step in approaching this problem. So what if we didn't have the Smith chart? So let's see how this goes. I'm going to include a visual aid here just so that we're not going to use the Smith chart per se, but I am going to kind of include this figure just so that we can orientate ourselves and get a sense of what we're trying to accomplish here. So the 2 points plotted over on the Smith chart here are our load impedance and our input impedance. The circle that you see here is the VSWR circle, and that was obtained by entering 3.1 into this little box here. So like I said at the beginning of the lecture, with series transmission lines, you want to think about rotations along the constant VSWR circle. So the first step is to figure out where the constant VSWR circle is. So if you recall, the VSWR is related to the reflection coefficient, and it's equal to 1 plus the magnitude of the reflection coefficient divided by 1 minus the magnitude of the reflection coefficient. So the distance from the center of the Smith chart to the VSWR circle is the magnitude of the reflection coefficient. So like I said, there's this intermediate point. We want to figure out what the reflection coefficient is at that point. Right now we're not interested in the phase, but in order to figure out what VSWR circle we're located on, we want to be able to calculate the input reflection coefficient, because we know that the reflection coefficient at point 1 here is going to reside on the same VSWR circle. So the first step is to figure out the difference between our input impedance and the characteristic impedance of our system. So I'm assuming that, maybe there is a 75 ohm attached to the input of this network here. So in this case, the input reflection coefficient would be the difference between the input impedance and the characteristic impedance of the system. So this results in a magnitude of 0.5145. So when you plug 0.145 into the equation for VSWR, it gives us a VSWR of 3.101, and you can see that value showing up here. So what this means is we have our load impedance here. Somehow we want to transform that load impedance to an impedance that corresponds to a reflection coefficient that sits on this VSWR circle. Okay, so I'm going to call that impedance Z1. So like I said at the beginning of the lecture, when it comes to the design of stubs, we want to be thinking about the constant conductance circles. So the first question that we need to ask is what constant conductance circle does our load impedance sit on? Because we can see here that we kind of have two paths that will bring us to that VSWR circle. We can either move downward to this location, or we can move upward to this location. So there's two impedances. Let's call them Z1 and Z2. Okay, so let's assume that we're trying to make it to this point here, and like I said, we're going to try to figure out what the impedance and reflection coefficient would result if we were to transform our load impedance to Z1 that sits on the constant VSWR circle. So let me just emphasize the fact that this is going to be a little bit time consuming. I don't expect any of you to ever go through this process. I suffered through it so that you would never have to. For the purpose of this course, I expect you to utilize the Smith chart, whether you are taking measurements manually or you're using software, like SimSmith or ADS or something like that. It will be your choice ultimately. But just bear with me through this example. I just want you to see how time consuming it is, to work through a somewhat simple problem like this without the aid of, a design tool like the Smith chart. So to go from here to here, I substitute the Euler's formula for the complex exponential, and then I invert these expressions because I know that Z1 is going to sit on the constant conductance circle of 0.8. So I needed to bring that number into the equation somehow. In order to simplify our lives a little bit, I'm going to make the following substitution where I let A equal, this reflection coefficient times cosine, and B equal reflection coefficient times sine. So that kind of simplifies our formulas a little bit. What I'm trying to do is separate the real part and the imaginary part from this expression here. I know that the real part is going to be equal to G here, and I know that this impedance sits on the G equals 0.8 constant conductance circle. So in order to do that, I'm going to multiply the top and bottom by the complex conjugate of this guy here. So if you multiply this stuff through, you end up with this. So after a little bit of rearranging, I'm able to isolate the real part, which equals this. So when I multiply these guys through and I multiply this out, I end up with this expression here. So then if I multiply both sides by what's in the denominator here, I end up with this expression. So remember that A equals the magnitude of the input reflection coefficient times cosine of the negative angle here. So if you substitute, and B equals the sine of that. So if you substitute those two expressions in for all the A's and B's in here, you get some cancellation. Simplifies a little bit, and you end up with the following expression. So in this equation here, everything is known. We know the G's, we know the magnitude of the input reflection coefficient. That's going to be the distance. That's going to be the distance from here to here. That represents the VSWR circle of 3.1, and we know G. So that allows us to solve for this angle. So when you plug in these values, you end up with the following angle. So an angle of 109 degrees represents a reflection coefficient that goes from the center of the Smith chart to Z1, and the angle here is going to be the negative 109 degrees. So we now have our expression for the reflection coefficient at this impedance point here, which sits on the VSWR circle of equal to 3.1. So from this reflection coefficient, we're able to calculate our intermediate impedance of Z1, which is equal to this value here. So again, we are at 0.1 here, where Z1 represents the load impedance transformed by a stub. And this impedance, Z1, represents the impedance that would be required to give us a reflection coefficient that sits on the same VSWR circle as our input reflection coefficient. Okay, so this is kind of where we're at so far. So the next thing we need to do is we need to figure out the geometry of this stub. I am saying that the impedance seen looking into the stub is going to be Z sub S. The input impedance seen looking into the parallel combination of the load impedance and this stub that we're designing is Z1, and that is going to be the parallel combination of the stub and the load. So that's kind of the next step, figuring out the length of this stub and deciding if it's going to be open or short circuit. Let's just somewhat arbitrarily start with an open circuit stub. So this is the impedance of an open circuit transmission line. So if you recall, in this expression down here, this is kind of the general impedance of a transmission line. If you set, well, I guess for a loaded transmission line, these two Z1 terms here would be ZL, the load impedance, and if you let the load impedance go to infinity, then the impedance will go to this expression that we have up here at the top. So that's where that comes from. We talked about that, I think, in lecture 1 or 2. And then, like I said, Z1 is going to be the parallel combination of the load and the stub. So if we take this equation for Z1 and we solve for ZS, we end up with this expression here. And since we know Z1 and we know what the load is, then we can figure out that the impedance seen looking into the stub is going to have to be minus J166. So we set that impedance equal to our expression up here for the open circuited stub, and then we're able to solve this expression for L, which is the length of that stub. Again, just to reiterate, if we have a open circuited stub that is 7% of a wavelength, that is going to give us an input impedance of ZS looking into the stub equal to this value here, and then if you put ZS in parallel with ZL, that is going to give us the impedance seen looking in at 0.1 here of Z1, and that's important because that gives us a reflection coefficient that sits on the same VSWR circle as the input reflection coefficient. So now the next step is to figure out the geometry of this series transmission line. So we start with our fundamental equation for impedance transformation along a transmission line. To simplify our math a little bit, we make another substitution. So we end up with this formula here. When we solve this formula for A, we end up with this expression. And if you look at all of the variables in this expression, we have the input impedance, which was given in the problem. We have the characteristic impedance of 75 ohms. And then we have Z1, which is the input impedance at this point here. So in order to transform Z1 to Zin, then this A term represented by this expression here has to equal negative J 9.9. So if we set tan equal to negative 9.9 from our expression for A, we see that because of this negative value, this implies that the argument of this tangent function here has to be negative. So if you recall the graph of the tangent function, it looks something like this, where this is pi over 2, and this is going to be negative pi over 2. So let's say this is the graph of tan of x here. And we know that the tangent function repeats itself every pi. So essentially what we're trying to do is we're trying to figure out where the tan of x equals negative 9.9. So if we use the tan of x given by this expression here, then essentially what we find is this x value here, which in this case is going to be negative, as you can see. So instead, what we want to do is figure out this x value. So in order to figure out what that value is, we know that the distance from here to here is going to be, let's say, x1, and this distance here is also going to be x1. So in order to be able to make the leap from this point x1 to this point x2, when we solve, tan x equals to negative 9.9, the distance between x1 and x2 is going to be pi. So when we solve this expression for x, we need to add pi in order to get a value for the length that makes sense, since x1 is negative. So I guess if I'm saying x1 is negative, then these distances are going to be the absolute value of that. Okay, so hopefully that's clear. So we make this horizontal translation of the tangent function. So this is going to give us 2 pi L over the wavelength equals pi plus arctangent of negative 9.9. And this gives us a length of the series transmission line of 0.26 of a wavelength. I know from the solution in the book that these two solutions here are correct, but let's just apply it to a problem here and plot it in SimSmith. So let's assume that we are operating at 2 gigahertz, that we have an effective dielectric constant of 4.0, and we're in a non-magnetic material. So with these parameters, the wavelength is going to end up being 7.5 centimeters. So if we plug in that wavelength into our two expressions for the series and stub transmission lines, we end up with transmission line lengths of 1.9 centimeters and half a centimeter.